Om Namah Shivaya. A very warm evening to everyone. It gives me immense pleasure to welcome you all to day 2 of the AICTE sponsored ATAL online 6-day faculty development program on semiconductors for smart systems, applications in IoT, AI, and next generation devices, organized by the Department of ECE in association with IQAC and IIC of Sri Satyam College of Engineering and Technology. Day 2 focuses on the theme Design and Tool, featuring two highly insightful technical sessions by eminent experts in the domains of semiconductor for VLSI design, EDA, and TCAD tools. We are delighted to have distinguished speakers with us this evening, bringing a wealth of both academic and industry expertise. Let us now commence with technical session 3. To introduce our esteemed speaker for session 3, may I now invite Professor M. Prishita Arati, HOD of Artificial Intelligence and Data Science, to formally introduce the expert.
Good evening, everyone. It gives me immense pleasure to introduce our first expert of the day, Dr. Jobin Varghese, Professor, Faculty of Engineering and Technology, Hillier College, QI Campus, Maldives. Dr. Jobin holds a PhD in robotics from MIT Calicut and an ME in mechatronics from Anna University. With over 11 years of teaching and research experience, his area of expertise include robotics, artificial intelligence, data mining, and machine learning applications in engineering and biomedical domains. He has worked on projects such as microgravity corrosion testing in collaboration with Maldives Space Research Organization and deep learning based lung cancer detection in Maldivian population. He has also received a startup research grant from Kerala Startup Mission and established a center of excellence in AI and robotics. We are indeed privileged to have him with us to share his insights on efficient semiconductor solutions for on-device AI in IoT systems. Sir, we are eager to listen to your session. Over to you, Dr. Jobin Varghese.
Thank you, Professor Prishita Arati ma'am, for the wonderful introduction of our expert. Now, with great pleasure, I invite Dr. Jobin Varghese to deliver his session on efficient semiconductor solution for on-device AI in IoT system. Sir, the session is yours.
Thank you, sir, for the nice invitation. I hope you can hear me, right?
Yes, sir. Yes, sir. Your voice is audible, sir.
Yeah. Okay, I'll make my presentation visible.
Right. Yes, sir. Visible, sir.
Yeah.
Please proceed, sir.
Thank you so much. So let me know if there is some issues with any voice, whatever be. Please let me know in between.
Yes,
the online session. Okay, so I have been introduced here, and I'm just taking a session on efficient semiconductor solution on on-device AI in IoT systems. So particularly, we know the latest technology, which includes artificial intelligence, Internet of Things, particularly. But there is something issue here is like the hardware should support the Internet of Things as well as the artificial intelligence to process. So this is something the world has the statistics, the calculations like 27 billion connected devices are there in 2025 worldwide on IoT. And almost if you see the market value, it comes to be $629 billion. Almost growth rate seems to be 24.6% from 2020, a 5 years gap. So it's a huge market of IoT. But in fact, there are multiple challenges here. So when I say the challenges, which has to be solved because of the limitation of multiple things as well. So if you say interoperability issues, like you have to communicate with different devices in different situations, and these connections make issues. Then device vulnerabilities will be there. There will be something like the weakness in the hardware and software. Then definitely we know the privacy concerns, because there will be multiple viruses like threats, ingroups, botnets, ransomware. All the things can attack and take the information from us. Security risk is another one. So we don't know how just the privacy works can be protected. So next comes other challenges include real-time analytics. So in fact, we know if we can process the data at the online and take the decision at the same time, like using an artificial intelligence or maybe the cloud-based like AWS, Azure, all the things can be used. So that is also a part of hardware restrictions comes to being to make it work. We have to always depend on the cloud basis still. If there is hardware that can work, definitely that will be a very good thing. Second is the power optimization, which is a major concern. So most of the IoT systems are working on the battery, and it is consuming a lot of power. So it should have the least power that should be taken to operate. Then next comes the data storage. So, every second, millions, billions of data are generating everywhere. And in fact, in the data storage system is another major issue we can find. The energy management, like monitor and control the energy consumption and distribution, as many IoT system works on battery power systems. Then regulatory compliances. The government will have many compliances, many rules, many policies, which has to be met and updated every time. So some other challenges includes the scalability. So ensuring the system can handle growing demands efficiently. So, a lot of system hardwares are increasing all around the world. And that all to be connected and to be controlled is a very tough task. Then the data volume is increasing, connectivity becomes a challenge, maintenance. So example, if you say a 5G system, definitely the connectivity becomes more, but it becomes more costlier as well. The technology has to be much improved when the population is increasing. And the other part of the things are like high upfront costs, significant initial investment required for the implementation of IoT system. Then there is a huge skills gap, like existing workforce lacks necessary expertise. And in fact, it takes time for them to get trained to that one. Talent shortages. So all these things, we come to the conclusion that there's a huge gap towards what we need to achieve and what is the current situation in this. So as a summary, if I say there is connectivity issues, there is a privacy issues, scalability, interoperability, security, then data storage problems, then there is talent problem. All the things are there still existing in this area. So we know the world is still striving towards the profession, perfectly how to create that. So the question here is why on-device AI matters for IoT? In the sense like why there should be a single system. In this one, AI should be installed and decisions should be taken. Such board should be there or not. So we have multiple screens, like we'll be mostly depending on the Raspberry Pi most times. But here you can see the first thing is reduce dependency, like minimizes the cloud reliance. I say AWS or maybe Azure. We always has to just depend on that one. That all depends upon the network bandwidth and network availability. Now, second is cutting latency. In fact, the data will be taken through the network to the AWS, processing, then return back. So definitely it will take a lot of time to take decisions. Those can be avoided, and operational expenses is significantly high as a subscription cost. Also, that is as per the usage we have to pay. Second is like the enhanced privacy. In fact, you have some images, the camera, maybe you can take an example as a CCTV camera. If you're trying to just transfer or just to analyze the images in the camera, if that is leaked, that can cause the privacy of a person, or maybe anything that is personal information can also be leaked. So that is very important. Then real-time decision, which is very much important here. So instant decisions has to be taken especially in the case of healthcare. So when there is an emergency comes for a human being, sudden decision, if we need to do sudden decision, definitely the data should be analyzed at a faster rate. Then only we can go for a sudden decision. Well, so I just introduce. I just introduced something called as Ambic Apollo 510, which you might have heard of the recent hardware which is into the market. So this can handle the artificial intelligence algorithms, particularly the video, the audio, definitely the other data can be processed with the help of model. So what are some of the important parts like exceptional efficiency have, simplified design, then versatile application. So when I say we will see it in detail on these cases. And if I just collectively say something, it's have a high performance, high efficiency, it's have leadership means like it could compete all other the hardware available in the market, and there's a thought output. So this is something like the view of this one. And this is a board. They have a development board. They have developed a chip here. So that is Apollo 510 and Apollo 510. The chip they have developed for this one, and they have a development board as well. And there are two variants. They have something called BGA as well as CSP. So that is having, so BGA with 183 GPIO pins and CSP with 144 GPIO pins. So everything is published in their websites, in the company's website. So we can even, like, its name is AMBIQ, AMBIQ, the reference I just added here. So they have another variant. Till now they were developing on the go, and you can see like there are multiple variants they have. So Apollo 510, which comes recently, and one of the comparison can we have this Apollo. You can see I just taken the Raspberry Pi initially. The reason is like Raspberry Pi is the one which will be using everyone, or maybe every campuses will be utilizing it. So you can have high power, it will be consumed, but in fact, in the case of Ambiq Apollo, it is ultra low microwatts to milliwatts. And battery life is very short in this case, but here have months or years IoT wearables. Then large, not embedded. So it is bigger when compared to this one. So it is tiny, easily embedded, drains battery fast, designed for always on. You don't want to shut down. Then security, basically there is advanced hardware security and moderate or high, very low in the case of cost. It's almost I hope like $13 nearly the cost for that. And when we just summarizing the comparison of Apollo 510 with the Raspberry Pi 5, you can see that is significant things like ultra low power, which is the major metric we will be using for developing any IoT system, and also not power efficient. So those things like when I say this one Raspberry Pi, always on intelligence, high computing capabilities are there for Raspberry Pi. But provided this is having the computing capability, and it's like not power efficient, it's power efficient, and ultra low power it is taking. So for IoT endpoint application requiring minimal power, long battery life, always on intelligence, tight integration, Apollo 510 is the superior one right now in the market. So this is the architecture of this one, which is displayed in their website. Definitely as similar to that, all this system for IoT, they have also developed that one. In fact, you can see the clock speed side, locking and timers, which is provided here. So which makes making things more faster. And what are the interfaces they have, the subsystems they have, memory subsystems. So it's something like 4 MB NVM and SRAM as 3 MB. It's given as the onboard. So this is already developed now. So now the part is like, what does this mean in some of the topics like the performance? When you say performance metrics, so evaluating the overall effectiveness and accuracy of the model means like when you deploy a AI model. So definitely we know that we will create the AI model, we will convert into a pickle model or maybe a job model. Then we try to deploy in Raspberry Pi, usually for face detection or color detection, whatever be the video or image detection, whatever the process it happens, we'll be doing that purpose. So that performance, like overall effectiveness and accuracy of the model, provided the processing speed is one of the things which determines the errors. Several times I came across there was multiple errors in a model, and in fact it was not cost of training or it's not the problem with something we made the model. It was clearly with the hardware. So the hardware were not able to. Raspberry Pi, I remember if I'm right, like or Raspberry Pi 4 with 1 GB RAM created some issues because they cannot execute. And later we changed the Raspberry Pi VC. So the performance metrics is very important. Then you can see inference as output, measuring the speed and rate of the model prediction. So how fast it can work, how fast it can give the result output. Then the other one is energy per joule. So very importantly, we have to say, because long time or long duration monitoring and processing definitely requires that this should consume less amount of energy. So we can say that efficiently should operate at a very low energy. Then model retraining. So I try to improve the model with the new data and feedback. So I hope this is one of the major things like we are saying. Once we train the model, even the ChatGPT does the same. It seems like initially they will be deploying the model further. Every ChatGPT will have a different character. When I use my ChatGPT, it will be giving me answer based on what prompts I am giving since I am training it. So similarly, if you have created an AI model and deployed, the AI model still should learn from the new data which is coming in, not only during the training time. So that training also take extensively computation. Extensively, they have to use the resources, and this resource should be optimizedly provided by any IoT system or hardware. Then only it will be working efficiently. So now again the question like, why does this matter? In the continuation, so we say something called the energy efficiency and performance. So when I say in performance, so performance gain, which is how do we measure? So one case is like we'll be measuring in terms of latency. So how fast it can work and with what less time period it can give the output. Second, how accurate it can work, like how the models when you check, like definitely we know when you take the artificial intelligence model, we train, then we test and evaluate, and we know if that is overfitting in the sense is it learns for the training parameter alone, then the testing accuracy will be lesser or evaluation accuracy will also be lesser. So in fact, that performance is how accurate, whether it can classify, whether it can predict, whether it can segment. So or whether it can detect, that's whatever operation it can do, particularly so accurately, the output should be calibrated every time. So that should happen is called the performance. The third factor is like that one, how low energy it is taking to compute to work. So that long time it can be energy efficient. So there is another issue with this type of embedded systems, or particularly this type of boards, they are creating a lot of heat. The fact heat ejections is another issue that is also not sustainable to the environment. So definitely that also should be taken as the performance parameters. And we have definitely the people who are using the industry they will be having something called operational savings, how to cut the cost, how to reduce so that it increase the profit. So whenever industry have a need, industry have interests, every technology will be booming out. So, and there should be higher energy efficiency for deployments. So there isn't a threat with heat generation, not only the environment sustainability, the electronics parts may also burn out because of this. So now we comes to the solution, since this is the one of the major hindrance for any development, as there is the hardware is performing much lesser. So you can say, like all the GPUs can have a 1,000 predictions per second. And you can see this one is having 300,000 predictions per second as by the new Apollo 510. So it is almost 300 times efficient when compared to the older GPUs. And you can see it uses 10 joules of energy here. It also uses the same 10 joules, but the prediction rate is much higher in this case. In an overall eagle's eye look, you can just come to this conclusion. So this is something more detailed about this 510. It's an advanced ultra low power microcontroller system on chip, specifically designed for high efficiency on device and IoT application. The leading edge microcontroller for an on device AI in IoT, offering industry best energy efficiency, robust AI ML performance, and strong security, enabling advanced battery powered smart device everywhere. So I remember I was using something called the Tiny ML. I hope this is from Ordino. So that is they have an embedded camera, they have embedded sound mic where we can deploy just for the students. It is costing about 5,000 rupees. So we can deploy some of the AI model directly into the hardware and it can be used. But the problem is like it will be very slow. The camera is much slower capturing, analyzing, classification, everything is slow. That is just as a test model that we cannot use it for any application. So from there, the development goes to Apollo 510. Yeah, we are still again going to compare something with the NVIDIA, the makers of any AI hardware or IoT, whatever be the hardware. In fact, they are in the front. Now, when it comes, Apollo has crossed that one with the NVIDIA. We will have some comparison. So some of the key features, if we see the key features of this one, definitely we say that, yeah, it's using ARM Cortex M55 with helium, then maximum frequency is 250 megahertz. On-chip NVM is up to 4 MB, as we have seen the architecture. So similarly, the processor used here is ARM Cortex. Similarly, what we are using in the computers, what we are using in the Raspberry Pi, the higher version. But here, definitely, there will be optimizations will be taking place in order to make this more efficient. And some other key features I just included in the slide so that someone can refer this. So these are the properties, the features which has been published in their website as they have just published their product. So almost definitely they have you can see in terms of processor, in terms of memory, in terms of air capability, in terms of power efficiency, in terms of security. Then in case of readiness and connectivity, it's working well. So you can see memory is up to 4 MB on chip, non-volatile memory NVM up to 3.75 MB, SRAM, plenty for AI inference and edge computing. So you can see in the Raspberry Pi 5, but the heating issue is much a problem in Raspberry Pi 5. So some of the applications of MBIC Apollo 510, you can see Edge AI for IoT devices. So you can see next generation wearables, health monitors, factory automation, remote sensors, AR/VR gadgets, smart homes, all running AI ML workloads locally. So even though the researchers are going on, everything is trying to make it optimize, make it faster, make it better. So industry should be the final one who is working on this one, who should get the benefit out of it, because all the development happens in the industry. So every research is focusing on towards how to develop that is capable to work in the industry. So industrial healthcare, consumer electronics, the real-time air force, speech vision, and more with minimal energy and high security. Definitely, this will also be used in home automations, particularly home safety systems. And if there is an emergency occurrence in a home where there are no people are there, or they may have went for it, they may went for a tool, or they may be out far away from the house, definitely they can control all the things with the help of IoT. But provided the system should be power efficient, should be more having higher performance in all terms. And if we are using something artificial intelligence algorithms, definitely that should be more accurate. And this is some of the comparison the Apollo 510 has given in the website. You can see Apollo 510 is used used in multiple AI workloads. So you can see keyword spotting, image classification, person detection, anomaly detection, and it says that energy use per AI load. So lower is better. So you can see that this is the y-axis gives you the energy used. So the lower one is better one, and you can see the blue color one like Apollo 510, which is represented here, having the lowest rate in energy usage. And there is another one, Apollo 4, and the other models having high energies utilizing by themselves. And also this is shown in the graph another way. So now we have to compare this Apollo 510 with respect to other processors who are the world leaders. So why we say that this is more better or having a high rank? In fact, recently, maybe tomorrow, maybe the next one may be coming, next company may be coming, but right now we can see this one. The Ambiq Apollo 510 is 30x better than legacy MCUs, 3x lower energy than the closest competition. So it is typically used for IoT sensors, wearables, always on edge vision audio. So the second, it comes to the Google Edge GPU. So Tera processing units are there. So you can see still higher efficiency, but still higher than Apollo 510 for ultra low power tasks. So it can also be used for cameras, smart sensors, image, audio inference. Then you can see Halo 8 AI accelerator. Then comes the NVIDIA Jetson Nano. Hopefully this will be known to many people, since particularly in the robotics will be using this one for deploying. And I have also personally used this one for deploying the artificial intelligence model for color detection and face detection. So, but when we take the case of performance wise, that is how much power it is taking, how accurate, how fast it can work, all the things, the NVIDIA Jetson Nano lacks much lower when compared to the Ambiq in cost as well. And finally, I have to compare something called as the STM. That is another company we're working. And in fact, that takes the case in the least. But in this comparison, if you see, for this, nowhere like the Raspberry Pi is taken. Actually, Raspberry Pi was not built for an industry. Definitely, that is done for working on the projects. That was the major idea. In fact, they have improved and versions are getting this. That is not for industrial operations. And you can see when you deploy some artificial intelligence models on that one, it's getting more and more heated up, getting more and more and getting more heating. And when your heat goes much higher, and if you're not cooling with like a fins or a fan, definitely the components will damage, as well as the algorithm will not be working properly. And this is just to show you the cost of this one. That is the Ambiq, which they have again displayed on their website as $14.12. So they are still in stock. As also you can see in ambiq.com. So now I just talked about these things, Apollo. Now the general discussion comes semiconductors innovations driving on-device AI. So when I say like ultra low power MCUs are the target, the specialized microcontrollers and system on chip optimized specifically for energy efficient edge AI workloads. So there is a chiplet architecture, which is very important in deciding the efficiency, performance of any chip. So also you can see advanced material is one area we have to work, because gallium nitride and next gen compounds improving power efficiency and thermal management dramatically. So these are some innovations driving on device on AI. So we have to focus on this type of innovation in order to progress further. So what makes these semiconductors efficient for AI plus IoT? So when I say these are some of the parameters or metrics that should be taken care, like ultra low power. So when we have some research or when we have some outputs, we have to prove that the one which is says consumes much lesser power than one is existing right now. Then it becomes significantly valid in terms, or you can say you have to integrate AI, like on chip integration should happen. It's not like connecting with the cloud and taking the results out. Rather, on chip integrate AI should be integrated, and it should also have something like detection, the video face image detection, video processing, all the things should happen. The tiny ML frameworks like TensorFlow Lite and Microframe for tiny RAM should be able to install and work inside this type of structures when we develop. And heterogeneous and open multi-core associates and RISC-CV for customizable efficiency. So like you can have an open source or can have an operating system. So those things should be efficient enough to work. So this is the way this is becoming more and more efficient. So provider, I say, like usually in general terms, we say low power, the higher, like the latency part, then low power consumption. Then it comes the performance. In fact, that should process the artificial intelligence models to predict correctly. So when you say the confusion metrics for the classification, these should give like the diagonal elements or diagonal part should have maximum inter count in order to get the maximum classification. Now, when I compare, this is something which I compare the existing one right now, including ESP32, Raspberry Pi, Pico, Nordic, like all the sources, like leading efficient semiconductor platforms. Usually we are using like Google Edge GPU, then NVIDIA Jetson, Origin Nano, Xavier, Helio, 8, Edge AI Accelerator, NXP, and ESP and everything is usually we are utilizing everywhere whenever we have to connect something wirelessly. And you can see the open source IoT MCUs like maybe like customizable energy smart chips increasingly used for secure IoT supporting both hardware and software ML acceleration. So that is the major part. Like you should have a software, you should have some firmware in that one that supports the ML acceleration. If you don't have an acceleration, definitely ML models won't be perfectly working. So why on-device AI for IoT? This is again this question, why we need this. So this was already discussed, but in fact it is more in detail. The reason is like reduce cloud dependence. So this is the trend where the world is moving. Like in fact, we are focusing to reduce the dependency of the cloud. The major reason is that if you want to use the cloud-based system, the internet connectivity should be well enough, and it may or may not be assured in all places. So definitely the reason, the second reason is like, in fact, you have to take all the data to the cloud, then get the result back, then we have to take the decision. So when we try to do these things, it takes enormous time to take a decision. Particularly if we are deploying something like for a patient in an ICU, so monitoring some patient in an ICU, in a fraction of seconds, everything can happen. So it should be clearly intimated to a doctor or the people that this person is in emergency, or something has to be done, should be done at a very faster way. So in fact, we will always remove the cloud usage. And if the cloud having some issue in its own, again, that will be creating some issues for us. So better to process the data locally so that we get a faster response without external servers. Second is something called the privacy and security, which is very much concerned nowadays. As you can see, we are using in the blockchain. We're making it more secure. So all the detail which is transferred, maybe you are transferring to a cloud like a AWS in order to process the AI model. Definitely, those can be hacked and the personal details can be extracted, and those can be leaked. In fact, that is also a major concern. So keep sensitive information safe on device. So that is another major important if you are taking on device things. Then third, like battery and cost saving. So definitely say like, suppose we are using definitely the embedded systems are developing, it will be using in robots. Definitely the robot will be having the embedded system, IoT system, so that it can collect the data from itself. And even in any places, even maybe there is a fire breakout or whatever happens, the robot can visit for the military applications. Definitely there can be some internet connectivity. They cannot be, there may be, may not be, all the things. In all these cases, the battery is one important part which we have to take care. So it was when I just talking about this, I remember a situation when we have a discussion here. Somebody was telling like, the ChatGPT is thinking, means artificial intelligence has the capability to think itself. So maybe as we have seen in the Hollywood films, there is a possibility that they will take their own power and do something and rule the world. So the main concern I was telling, like, yeah, whatever it happens, if you switch off the battery, everything is finished. So till the battery is available for a robot, it can work, it can think, it can do. So battery is a major concern for any devices, particularly when I say like independent or something like IoT device, which we are not using with a power source. That is the onboard SOCs we are using onboard things, then battery is a concern. Second is the cost, like the cost, in fact, like we are using some others, cloud hardware, all the things, where we have to rent it. So these are the major focus why we should go to a on-device AI for IoT. Why not we can depend on the cloud, and major focus of my topic is also this one. Why should we go to a on-device AI for IoT? So hopefully you might also have heard about something like intelligent IoT system. Definitely there is industrial IoT systems, IIoT we say, but intelligent IoT systems where we collect the data and finally we take decisions based on the data we achieve. And AI is a must for taking decisions, and collecting data, IoT is a must. So when it comes to the latest trends and innovations, you can see energy harvesting AI. So you can see self-powering AI for sustainable off-grid operation. So you can see there is like you're using AI from vibration, energy from vibration, solar, RF, making truly autonomous AI nodes. Because depending on a power source like a battery, definitely has to be charged in the meantime. So if you can think of something like a hybrid, where we can develop or we can charge these things on the go with the help of some renewable resources, or maybe because of some vibrations, like usually we can apply some piezoelectric things which can create some current. So many other methods are done like that, those because the vibration, or maybe from the RF, all the things, if it can charge it can create itself, then that will be a good method. That is the trend in which world is trying to find. Second is like you can see the autonomous AI edge nodes. So independent device for remote data collection and processing. So when I say usually we do that, we will be using a mobile phone in the camera, or maybe installing some type of app, and in fact, multi-purposely we are using rather than this particularly make some AI nodes or AI devices which can work autonomously. And one of the applications we might be coming across is like the when the wild animals is disturbing human life in the border of some forest. Definitely, they can have some autonomous system there, so that it can identify from, or it can just record the sound of the animal and find out some attacks is coming, or it can also develop some type of sounds and create them away from the place. So all these things need an autonomous AI nodes, provided there should be a battery issue, and that should be we should find some power source for that. Third one is like integrated secure elements. So like built-in hardware security for robust data protection. So there should be like the security system. When you transfer this one, the protocols definitely, if you can save that one in a like a memory card, and later if when requested it is sending to the server as required. So those things can also be done, like the data becomes more higher. So onboard systems can help, or maybe additional memory system can also be helped. Then it comes modular, scalable, like flexible chipset that adapt to evolving system needs. So like you see the system on chips. Usually when we install some chips, definitely that is static, that cannot be used or cannot be expanded or cannot be made for another work. Unless otherwise we have another device on the board. So the chips should have some flexibility so that they can adapt to the evolving system. So these are the focus the world is looking towards, the trends in the innovation where the IoT system should go. And initially, we are also have seen many challenges, definitely, that also has to be taken care. Now, when I say something like so whenever a technology is developed, whenever something is invented and it is funded, definitely, that is very much focused on the market trends. And if there is no demand for that product, nobody is going to invest and nobody is going to work behind it to develop that, until otherwise there is a cutting edge technology come out of that. So when I see this IoT, it has a drastic growth. So you can see on device AI market expanding at 24.6% CAGR. So you can see 124 billion by 2032. It's a projection. Even from 2020 to 2025, the number of devices connected is also increased. There is also compound average growth rate you can see from 2020. It's multiple time as compared to what is in 20. So in 2032, again, you can see $124 billion the market is going to reach for this IoT system. So there's an explosive growth. And in fact, there will be a lot of job requirements in this field. Since one of the challenges they facing is the low skilled people, the challenge in this area. Second is like a smartphone leadership. So semiconductors rules right now because of the semiconductors growth in 1900s after 1950. The growth was much higher, which leads right now to the artificial intelligence, which is on chip processing methods are also being developed. So mobile devices command 46.2% market share, driving rapid innovation in AI-capable chip architectures. So you can see like the market share is almost half for the smartphone leadership. So many are occupying this one. So it is quite easy for us to have a something like a device for this, an enhanced capability. Now there comes the federated learning combined with 5G integration dramatically improves edge AI responsiveness and security. So as you know, when the generation increases, we know more bandwidth it can accumulate and more speed is increasing. So the data transfer will be very faster. So again, as the network speed, network bandwidth is increasing, the world is focusing on that one. On the similar way, the IoT is also moving in the same direction. So there is a very good growth in the upcoming era for the IoT. So almost projected, we know 24.5% is CAGR in 2032, and by 2050, it may be more than 50. So when it comes to like the real world applications, so you can see from hearing aids to autonomous system. So whenever we need, for example, recently we have heard like the chip is installed in the brain, the human being. So definitely that is all the part of embedded systems development, and the chip should be much, much smaller, but it should be highly efficient, less energy taken, and this will self autonomously charge. All the things are required when you try some chips in your body or maybe with the human being. So right now, when you see the healthcare revolution, Apollo 510 MCU powers OTC hearing aids with speech enhanced AI, dramatically extending battery life while improving user experience. So you can see this one, the hearing aid is supported by Apollo 510 MCU because of the smaller size form factor. The autonomous operations edge AI chips enable drones, smart grids to operate ultra low latency and exceptional reliability. Then industrial intelligence, IoT device leverage on device AI for predictive maintenance and real-time safety monitoring system. So once we are also trying with um, like different type of embedded systems. So we are also trying with something like Raspberry Pi. Then also many chips were using, but in fact many have their drawbacks where the processing becomes much lesser. The risk was also creating issue. Okay. Then now we are thinking of challenges and opportunities ahead. What are the challenges? What are the opportunities? Definitely, if you apply your technology into the time where there is an opportunity, definitely that's the time where we can grab maximum. So you can see the supply chain tensions are important. So geopolitical factors and manufacturing constraints impact AI chip availability and pricing structures. So we remember recently there was a shortage for the chip because there are many countries like Taiwan or was not producing enough chips. Only that place was supplying to the world, but they could not supply enough quantity. As a result, there was a shortage. And in fact, because of the shortage of the chip, the automobile, which is completely using this type of chip, the prices has gone much higher. So everything, the price has gone. So because of the supply chain tensions, that is the key challenges. If India does not have a facility to develop or create the chip or this type of embryo system, we have to depend on other countries. Definitely, they have to transfer things, and it becomes key challenges based on multiple things like the government policy, maybe supply chain, maybe any other factors can affect this case. Then the size and power constraint. So I can say, as far as we can reduce the size much lesser, so it becomes more and more compact. The systems can be made more and more compact. And when it's more and more compact, it is adaptable to different area, particularly in the healthcare as well. When the size is much reduced, it will be better for using this. So second is the power. Even when you reduce the power, reduce the size, there is a possibility that it's increase in heating happens, or maybe the similar the electronic components, the transistors, or the methods which we are working on. The what do you say, like MEMS technology, everything has to be improved so that we can get a small size and high efficiency. Then third one is like security. So these are the key challenges we're working on. Security imperatives. So growing demand for hardware level security, protect edge AI system from evolving cyber threats. So very simple example, if you just think of the mobile phone. So definitely that's an edge device. In fact, that is not autonomously working for a particular thing. It's a multitasking thing, but still it can also be considered. So there are possibilities. There is some privacy can be broken because of the mobile phone. We'll have our own photos or have our own private things. Everything can also be leaked out. So definitely that is another security concern. So these are the key challenges. And in fact, when we have a challenge, we say there is a challenge, there is an opportunity. There is a challenge, there is opportunity to develop. How to solve it. So different technologies can be used in order to solve this type of thing. So it says like the right here, it says from website is Statista. It says that distribution of the global semiconductors fabricating capacity in 2022 by location. And if I just closely see, this is the statistica of 2022. It is computer in 2022. And you can see Taiwan producing almost 22%, China by 22%, South Korea 25%, Southeast Asia 4%, Europe and Middle East 6%, Americas 8%, Japan 30%. So you can see the mostly made by South Korea, then followed by China and Taiwan. So last time there was a scarcity. In fact, everyone was looking towards the Taiwan because they were having the source. They were having a lot of manufactured chips were there, but in fact, they cannot supply to the whole world. So others were having the shortage for the materials also. So now the future. So seamless AI everywhere powered by semiconductors. So when I say neuromorphic chips, and also you can see in the computers, latest computers when you purchase, you can see there are processors that is used for artificial intelligence particularly. We were using GPUs already, so where it can handle the maximum number of tensors. So now we can see something called as NPUs. So NPUs, in fact, that is focused more on just computing the maximum. And hopefully, you might also have heard of quantum computing. So quantum computing, in fact, this is also required the processing power. The computation has to be done a lot, but it's optimized the way the computation happens. But still, it depends upon the hardware. So again, the hardware development is a must when we look forward for the next technology. So you can see, I was discussing here, neuromorphic chips. So you can see next generation architects mimicking the human brain efficiency. So that is the major challenge the scientific world is trying to solve right now. Although they could reach only a certain percentage to achieve how the brain works or how to make as efficient as the brain models. The neural networks also working on that. So brain efficiency is something different. And if you want to achieve that brain efficiency, something like the quantum computing should come, like 80 million neurons has to be working in the brain similar way the quantum computing works. And if the quantum computing has to work in IoT system, definitely we should have a better efficient embedded systems or SoCs, system on chips, all should be developed. So second is semiconductor innovation, like foundation enabling ubiquitous, efficient on-device AI. So 5G integration, autonomous ecosystem. So this is another part I say, like I already discussed this one. Anyhow, self-learning system that adapt and evolve continuously. So this is one of the area where we work on that AI system. The reason is like when we deploy some AI model and if you are using in some area, for example, I will say that for the traffic will be just established or we are deploying some camera, a camera, but the camera might be trained with the images in a lab, in a laboratory by collecting the details. But when it comes to the real environment, every day different activities are happening in the road. So the camera could able to identify someone who didn't wear the helmets, or maybe somebody who doesn't use the seat belts, or somebody who is in a very fast. So all the things, traffic violation can be identified, but there will be some other non-linear things, regular things can also happen. So that if that is not trained, the camera should be able to learn from the real environment. So there is an autonomous ecosystem, how fast it is working. So usually when we create the AI system, we have a trained data set, we have a test data set, we have validation data set. So these all we take from the history, like already from the past, we will be taking, we are splitting and training. So this is only the past experience, not the current experience, or maybe that's not the future experience. So that should also be included and should be tested. And particularly the Q1 channels, they are focusing on this type of things in the real world, how we can work on. The convergence of AI, 5G, and IT technology is creating intelligent autonomous ecosystem that will transform every aspect of modern life. So remember one thing, like we cannot sustain or we cannot achieve any goals with a single technology. So there should be a convergence, there should be a cooperation, there should be a synchronization of different technologies. So the latest technology, as you say, there is artificial intelligence, we have a 5G, IoT technologies, which can create intelligent decisions, which can take the intelligent decisions. And if we want something to be acted, definitely the robotics should also be in this area. Physically, something to be achieved, definitely we should also include the robotics. On the other hand, in fact, to collect the data, take decision, and like it can be have a good communication. Definitely AI, 5G, and IoT can join their hands or can be converged together in order to make things. So the convergence comes only when it is on a system on chips, or maybe in a single platform. If we can work on artificial intelligence, IoT technology, and 5G technology in a single platform or single board, if it can develop, then definitely this can come to converge. So that is Apollo's focus, Apollo fight, ambiguous focus. So I have used some words called the 5G. There is something called a distributed intelligence. So I just want to note this one: seamless connectivity enabling distributed intelligence. So what is distributed intelligence? So it's the principle spreading of computational intelligence so that decision making, learning, and problem solving happen collectively across a network of agents, devices, or people. This makes system more efficient, robust, adaptive compared to traditional centralized intelligence. So we can see that it is being spread. The problem solving happens collectively across network of agents, devices, or people. So there is a lot of people come together, the system come together. There is something which comes all together, convergence, in order to compute the things and create the intelligence. Definitely this will help for a better performance. So it says like, just taken this one shortly, like local decision making, empowering individual nodes to make autonomous choices, collaborative learning, sharing insights and knowledge across the entire network, ensuring system resilience and continuous operation, adaptive efficiency, dynamically optimizing performance based on current conditions. So in this case, you can see not only the things like network of agents, devices, people are also being a part and be a part. So when I say something called the agents, now the artificial intelligence field is full of agent creation. Agent creation, in fact, we are creating something for a specific task, specific work, like automating the Gmail or creating some bots for maybe answering our calls, messages. So those things are agents. Now, you can see I'm also again going to the future technologies, like how it is further working. So transformative technology solution like AMBIC, Apollo 510 are revolutionizing IoT AI capabilities with unprecedented efficiency. So, there should be a competition should happen. When we have Apollo 510, which developed with this capability, definitely the competitors like NVIDIA we'll be working on in order for the developing the next one. So as everyone is competing, the technological usage or the coverage becomes more and more. So new possibilities include like, the on-device AI unlocks innovations in privacy protection, latency reduction, and energy optimization. So this is like we are not depending on any other sources. We are depending on single source in order to do all this. And future investment, semiconductor innovation is essential to realize the full potential of intelligent IoT system. So that is the core of any IoT system is semiconductor innovation. What materials can you use in order to mask and develop these things, or what mask you can use, what materials you can change in order to make the technology better, so that we will get an efficient semiconductor which will consume less amount of power and which can perform better. That is the major or the root of any IoT system. So future of IoT lies at the intersection of semiconductor efficiency and artificial intelligence, creating a world where every device is intelligent, responsive, and energy conscious. Again, I told you the words which comes here, like very importantly, we have to see on the energy consciousness, responsive or the performance, how the output comes, and it should be intelligent, like a human being, something on board, it is working as a intelligence. Now I come to the part of this almost discussion on this topic, and so it's something I have to discuss something on some research gaps. Since I was talking totally of the industry, what about what is happened in the industry, what is the current scenario of the industry, how IoT intelligence is included here. So I want to just discuss some of the research gaps in somebody who would be like to research in the area. Definitely the gap is very important in research, since the novelty comes from the gap, and the gap should be filled, and many journals will be accepting based on clearly addressing the gap. We can address the gap better acceptance and better admiration will be on. So when I say how to display on another document, so I prepared some of the metrics, which is also similar to what we discussed about the industry. Okay, so there are some potential research gaps we could identify. It's like energy efficiency metrics. So this is by ATAL in 2021-22. Models propose various models, but do not converge an universal metric, leading to inconsistency in the comparative analysis. So you can say existing literature offers lacks in standardized metrics for evaluating energy efficiency in semiconductor solution for on-device. So how do you evaluate the energy efficiency? How do you say based on the works? In fact, the computation model is more hectic or more require more computation, and if you are comparing with another model which is not having much computation, or maybe another reasons will be maybe the sensor which is connected will be consuming more power, or maybe some other device is taking more power. All the things are not even standardized or even methods to evaluate. So it is one requirement, energy efficiency metrics. How can you measure the energy efficiency when you integrate AI in IoT system? That is the part. When you integrate AI in IoT, definitely there will be methods of that. When you integrate AI, different AI models have different requirements. How do you quantify? How do you find the methods to measure? The second is like integration of AI algorithms and hardware with hardware. So how do you integrate? So the model, as we know that when we work on segmentation, medical images, the models are becoming more and more complex. So how can you integrate that one or deploy that one? So the gap is that there is limited research on seamless integration of AI algorithms with semiconductor hardware for optimized performance in IoT applications. This is the gap. Particularly in IoT application, how can you integrate? So there's also based on some research. Second is, third one is the scalability of the semiconductor solution. So like most studies focus on single device performance, neglecting scalability issues when multiple IoT devices are deployed. So single, like we only create for a particular ICU, we only create for a particular home automation. So if there is an integration, what happens? Those studies are not being conducted at. So there are most studies not conducted, but there are few studies. So they are neglecting the scalability issues. Then adaptability to diverse IoT environment. So the gap says that there is insufficient exploration of how semiconductor solutions can adapt to varying environmental conditions in IoT deployments. Again, that comes to the deployment part. So definitely the heat can affect the temperature, the humidity. So all the environment, the corrosive nature, everything can be a reason for having a lesser performance. So that is not even explored in different environmental conditions. Then security implications, like the gap is the intersection of semiconductor technology, on-device AI, and security in IoT system is under-researched. So intersection of semiconductor technology, on-device, particularly we say on-device AI, and security in IoT system is under-researched. Because we are trying to develop the models or the chips which can have a high energy efficient, which can have less power, it can take more computation, low cost, all the things you are focusing on development because that is the industry focus. But research has not been happened in this area on device AI, how we do. Then long-term reliability of semiconductor materials. There is a lack of longitudinal studies examining the long-term reliability of new semiconductor materials used for on-device AI in IoT systems. So what happens? What will be the effect if you have a long-term reliability? What is to be proposed and how can you prove? Like what other things is going to happen in the future? Maybe if you have a lot of silicon. Next one is AI model compression techniques. So this is an important part, like even we are also challenging, like when we go into deploying this one. So you have to compress the AI model so that the size of this will be lesser. And that can also help in deploying it on any device, in any edge devices as well. So research on effective model compression techniques specifically tailored for semiconductor constraints in IoT is sparse. So that is also important how we can compress a high-end model so that we can use independently. It can be used in different fields. So we can use in different fields like a medical field as an independent device. Those things also has to be explored, not explored. Now we comes to quantum computing. So this was I was talking already about the quantum computing on semiconductor solutions. The potential impact of quantum computing on the future of semiconductor solution for on-device AI in IoT is not well understood because the quantum computing field is still under development since we have a lack of processors, we have a lack of computation capability. The quantum computing is still struggling, the development is still struggling. We can apply for something with the help of GPUs, but still its full potential to not be achieved until otherwise the computation device with the semiconductor is improved. And there is something like user-generated design approaches. Sorry, user-centric design approaches. There is a need for research that incorporates user-centric design principles in developing semiconductor solutions for IoT AI applications. So user-centric, that should be for maybe for like say somebody in the ICU or maybe somebody in a shop. It can be somebody in some working area. particularly that is for that particular customized based of use or based on which user it is used. Everything is generalized. Everything is generalized bringing, but not specific. Researches has not been done on any type of application till it under development. Next is cross-disciplinary innovation. So the limited exploration of cross-disciplinary innovation combining semiconductor technology, AI, and material science for enhanced IoT solution. So it will have a combination of semiconductor technology, artificial intelligence, and material science, type of materials that you can work on. If you change the material, what is going to happen? What will be the benefit? What is the effect? So all the things are still under development. Definitely, I already have shown you like 24.5% CAGR will be grown by 2032. So the growth will happen in IoT, artificial intelligence, 5G systems. So all the things are developing. So the intensive research will be taking place in the upcoming years on this field, so that only the industry could achieve what is what they require. So definitely we know AI has created some revolution. Yeah, we can say it's like a revolution. Clearly, a revolution has been taken, has been conducted or made. So IoT is the next stage where it's going to support AI and make a huge development. So this is some of the opportunities I have shown you. There will be multiple opportunities, but I didn't take all the opportunities. But I have taken only listed 10 opportunities from different papers on in this field. And definitely chip development, increasing the energy efficiency, all that requires the facilities. But there are some area where we can work on, which does not require something very new or maybe the computation power, but to explore the area. Like for example, I can say, yeah, this is one area you can see neglecting scalability issues when multiple IoT systems are developed. We don't want to improve the IoT system, but we can utilize multiple IoT system. What is the effect is going? Then you can. The second one is how this adapt to environmental condition. It's another one which is possible to study. Then it's like, yeah, this also can be if we have less security ideas or security area if you'd like to explore. So long-term reliability of new semiconductor studies to see how it can be explored. Definitely, this is one important area where we can compression techniques, since we can use multiple softwares to compress and algorithms to compress that one and try to deploy in the IoT in a processor. So there are multiple methods we can work on in the research area as academician, and definitely the industry and the whole world is supporting that also. So this is something like research gap as academician can be utilized, or maybe for industry. And less energy efficient and the technology adaptability are the focus of industry. For academics, there is something to explore, to understand about what is not explored. So this I taken from some of the websites, majorly product websites, also from research articles in that. So that's all I have to say on this part. And I have to give one more input, like, if you're trying for any type of Q1 journals or tutor journal, maybe Scopus or Web of Science, the gap should be clearly analyzed. There should be a novelty in the sense something which is not made should be incorporated. That is the first and major thing required for publishing. So novelty, the gap should be clearly identified, and definitely there will be a limitation for any work. So that should also be specified. That you cannot do all the works in a single process. That should be specified. So first is the novelty, that is the gap, find the gap, then work on it, then find the limitations. Then all the things definitely should be there, but these are the things that should be taken much care. Otherwise, the limitations are the area where the other future works can be done, or we are giving input to the next researcher what you can work on. And that's all for the today. Thank you for listening. I just come to my end of presentation.
So thank you, Dr. Jobin Varghese, sir, for that deeply insightful and technically enriching session. To propose the vote of thanks for this session, may I invite Professor C. Sasikumar, HOD of Computer Science and Engineering, to do the honors.
Good evening, everyone. Thank you very much, Dr. Jobin Varghese, for your insightful and thought-provoking sessions on efficient semiconductor solutions for on-device AI in IoT systems. Your deep technical knowledge, practical illustrations, and research perspectives have greatly enriched our understanding and will undoubtedly benefit our participants in their academic and research endeavors. On behalf of the Department of ECE, IQAC and IIC, we express our sincere gratitude to you for accepting our invitation and sparing your valuable time with us this evening. Thank you once again, sir.
Thank you so much.
Thank you, Professor Sasikumar, sir, for your kind words and for proposing the vote of thanks for this session to gracefully. I request all the participants to stay online for technical session 4. It will be start sharply at 7:30 p.m. So before that, I will post the technical session 3 feedback form as well as queries detailed contact in our chat box as well as WhatsApp group. Thank you. Our distinguished expert for this session, may I invite Dr. R. Hemalata, HOD of Biomedical Engineering, to introduce the speaker.
Thank you, sir. Good evening to one and all. It gives me immense pleasure to introduce today distinguished resource person, Dr. L. Arivalagan, Principal Engineer at Global Foundries, Karnataka, who will be delivering a session on EDA and DCAD tools in semiconductor circuit design. As part of our faculty development program on semiconductors for smart systems, applications in IoT, AI, and next-gen devices, organized by Department of ECE in association with the IQAC and IIC. Dr. Arivalagan has rich industry experience in semiconductor circuit design, working with EDA and TCAD tools. His expertise includes the use of leading industry platforms like Synopsys, Cadence, and Silvaco for semiconductor modeling, analysis, and simulation. This session will provide valuable insights into practical aspects of circuit design using advanced EDA and TCAD tools, which play a crucial role in bridging the gap between design and fabrication. On behalf of our institution and organizing committee, I extend a warm and cordial welcome to you, sir. We are looking forward to an enriching and inspiring session. Now, we hand over the session to Dr. L. Arivalagan, sir. Welcome you, sir.
So thank you, Dr. Hemalata ma'am, for the warm and insightful introduction of our expert. Now, with great pleasure, I invite Dr. L. Arivalagan sir to deliver his session on EDA and TCAD tools in semiconductor circuit design. Sir, the session is yours.
So thank you, sir. And thank you, Dr. Hemalata, for giving a brief introductions. So thank you, one and all here. So let me share again. Sir, hope my screen is visible. Is it, sir?
Yes, sir, your screen is visible. Kindly check whether the slides are moving or not, sir, please.
Yeah, sure.
Yes, sir. Now it's okay.
Yep. So it's about the EDA and the TCAD tool for semiconductor device and circuit. So this is content. So I'll talk about what are the ADA tools, just the list. Then primarily I'll talk about on two things. One is ADS and then the TCAD. So the ADS is the circuit and layout simulator. So in that I am just to show some basic info how the simulator circuit is going to be fabricated in industry. Then how can we do parameter extractions and modeling in the ADS tool. So that's the thing. And then the second is the TCAD tool. So this is a semiconductor devices simulator. So here I'll explain device simulations, and also I will explain how we can mimic a circuit in a TCAD. So it's a kind of, I'm not going to give up like a hands-on training. I'm going to give some essential part. How can we use these tools in industry as well as in the research? So that's the main focus. So these are all the tools actually. So EDA, we have Cadence, Mentor Graphics, Scale Layout, ADS, AWR, etc. So I just listed some. Then the TCADs, we have Synopsys and RS, then Silvaco, then Crosslight, Upsize. So these are all the TCAD tools. So this is used for the device design. So on the other hand, the EDA tool is used for the circuit as well as the layout design. So here just I just give us some background about the simulations. So why we do a simulation? So for example, if you take the left top figure, you can see two persons are measuring some distance. So this is a physical measurement. And then there are some scenario, radar, black hole, the distance from the Earth to Sun, then sonar, IR, then something like some birds inspired story that is fetched to the technology. So simulation. So let's take the black hole. So we know the black hole. So the latest image was released by the NASA. So so we can imagine like how can we take a picture of the black hole. So is it really possible or not? For example, we cannot go near to the black hole and take a picture of it. So it's not possible. And then if you take some radar, so it is used to identify some objects in the air, like a fighter jet or bats, etc. So if you want to measure some speed of some flying aircraft, we cannot easily do by manual. Then if you take a distance between the sun to earth, it's also difficult to measure because we can't go near to the sun and then we can measure it. Similarly, some detecting submarine inside the ocean, then detecting some temperature on the persons. So all these things having some limitations. Then measuring distance. So measuring distance also is not easy when the object is very far or it is a very very fast. So in every real experiment, we have our limitations and we can't measure something. And apart from that, there are few more things. When we do something, some measurement, or when we develop some product, there is a time and cost. So for example, if you're making a device, so that will take 4 months or 6 months to be fabricated. So we have to wait around 6 months. Some engineer need to be work for 6 months. So we can imagine 20 engineers are working in manufacturing a device, and you need to invest the time. The simulation help us to reduce the time and to reduce the cost. That is the main thing behind this simulation. Then the limitations. We can't measure something. like this black hole, and we can go near to the Earth to Sun. So these are all some limitations where the simulation will assist us. So I just moved to the ADS one. So in the beginning, I said there are some tools, ADS, Cadence, AWR, etc., that can be used for the circuit simulations. So here, the circuit simulation to the manufacturing chip. So we can imagine how we do an experiment in a laboratory. So we do some connecting components, and then making a circuit, then we check the circuit, then we do a measurement. So this is what we do in a real laboratory experiment. Even if we take some the undergraduate program, we can do this. So the same thing we will do here as well in the simulation. Here also we pick some component, we will connect them, and then we will check whether they are correct or not. So when we do some experiment, we should know something like this. For example, if it is a circuit, we should know the branch, node, some laws like Kirchhoff's voltage law, Kirchhoff's current law, and also some function of a semiconductor device like a diode, transistor, etc. Then gain, cutoff frequency, what is the feedback circuit, and what is input, output, supply. So all these things we should know. So if you have some basic knowledge how we can do an experiment in our reality, we can do a good simulation as well. So that is the story. So here, how we convert the simulation circuit into a manufacturing device. So initially we do some circuit simulation. If you take some ADS tool, there will be options like schematic window. So we can draw our circuit there. Then we will link this circuit to the physical layout. Then we do some verifications are they correct or not. Then we will make a manufacturing output. So this is called a tap out. So this tap out can be directly given to the fabricating equipment. So that will fabricate the device. Then we can measure the output parameters like current, voltage, S parameter, Y parameter, etc. So this is the flow that is happening in the industry. So in the ADS, this is schematic window. So this is more like a SPICE tool that we use in our bachelor degree. So it will have some elements like a resistor, transistor, capacitor, and also it will have devices, a diode, transistor, etc. Then we do connections of this element, and then we will fetch to the layout one. So here, all this connection will be like a converted into a script. So that's called a netlist. So this is just a description how the component are connected. So this is the schematic window. Then when we do a circuit simulations, when we draw the circuit and we give to the system, so what will happen inside the system? So how the simulation is carried out. So it's all about model. So for example, the SPICE model we can divide into like a device model, then sub-circuit model. In the device model, we have different devices, BJT, diodes, MOSFET, etc. So they also will have a models. So model means like in our electron devices subject, we can see some diode equations, some H parameter equations, some IDVG, IDVD equations we can see in the subject. So all this equation is solved behind. Apart from that, there is a sub-circuit model. In the sub-circuit model, for example, if you do an experiment, for example, in a diode, we vary the voltage and we will measure the current at 25 degrees Celsius. Let's imagine like that. So in that, there are temperature effect. If you want a temperature effect in the simulations, we have to use some thermal models. And for other devices like IGBT, silicon carbide, etc., we can use some equation-based models. So model also can be classified like a physics-based and then empirical-based. So empirical-based means it's a fully equation with a lot of fitting parameter and does not carry any physics. So that is a empirical model. So the physics-based model will have some percentage of fitting parameter and some percentage of physics. So once we create this schematic, once we have drawn this circuit, we can link to this layout. So this is a layout, and we can have the options to link this element from this schematic window to layout window. Once we done that, we can check it. So the connections are correct or not. So for example, when we do a laboratory experiment, we do some short circuit or we miss some connections. So these kind of things will make some error in the simulation. So it's almost closer to the real experiment of video simulation. Then when we use this verification, some component will take wrong models, and then sometime it will ignore some ambient effect like temperature, humidity, etc. So we can check everything. So that will be listed in the verification. So that will give us the direction how we can fix the issues. So then this ADS parameter extraction and modeling. So this is one of my work. So here just in the right side, we can just, this is an field affected transistor. So here I'm just putting a GaN hunt. So it's a kind of a MOSFET. So it has the source, gate, drain, etc. And then some active layers, LGAN, GaN substrate, etc. So the channel is formed between this LGAN and the GaN interface. Okay. So the right side, we are seeing a 2D layout. In the left side, we are seeing a circuit. So both of them are same, but modeled in a different way. Right one is a structural based or a layout based. The left one is a circuit based. So both having the capability to define or describe a behavior of the MOSFET. So this is a small signal circuit. So this can be called like a small signal circuit or large signal circuit. So in that we will have our elements like a resistor, capacitor, inductor, and then some active element as well. Here there is something IDS, that is a drain to source current. So when we do a simulation, so in the right side also we will terminate by 50 ohm, and then left side we will terminate by 50 ohm to do a simulation of the circuit in a ADS. Then the ADS also having the S parameter simulation controller. So that is used to sweep the frequency. So we will sweep the frequency and then we will measure the S parameter. Then we can also measure this noise parameter as well. So in this work, like, so I was using a small signal circuit simulation that is assisting for the TCAD one. So once we have this experimental data, the characteristic data, we can get from the experimental data, we can have the S and the N parameter. S is the scattering parameter, N is the noise parameter. So from the noise parameter, we can extract the parameters. If you look at the S parameter, it is just a complex number. So in the complex number, we can extract the capacitance, we can extract the resistance, we can extract the transconductance, inductance, and everything. Then we can extract the parameter that can be used in the ADS circuit simulation. Then we can do a noise simulations. Once we do the noise simulation, so this is one branch. In the other side, similarly, we do a device simulation. There it's just a geometry, physics, then device assimilation, then simulating noise figure, and we do a comparison. So if the result of the small signal circuit and then the TCAT circuit are equal in the sense, then our TCAT simulation is correct, because the left branch is coming from the experiment. In the right side, it's taking some geometry and physics. In the left side, it's purely taking some measured S parameters. Okay, so how can we do a parameter extractions? So first, we need to convert this S parameter to Y parameter. We might have studied this in some network theory, like we can convert this S parameter to Y parameter, S parameter to Z parameter, H parameter, etc. Once we convert this S parameter to Y parameter, then from there we can extract the capacitance. Okay, so in the previous slide, you have seen this is the circuit. So we can imagine if you apply the low frequency, what will happen to this circuit? So this will simply become a capacitive circuit. So in the low frequency, capacitors are open. In the high frequency, the inductor are shorted, so that we can short all the inductor, and we have only this capacitive element. So this is the equivalent circuit. Once converting the S parameter into Y parameter, we have these elements like Y11, Y12, Y21, etc. From there, we can ignore some element which is not associated with the frequency. If you look at these equations, you can see there is a JW, sorry, J omega. So from there, we can extract this capacitance. So simply, if you find the slope of frequency versus magnitude of Y21, we can measure this gate to drain capacitance. And then if you want to measure the gate to source capacitance, we can use Y11. So then de-embedding. So de-embedding means when we go for the conditions like a high frequency conditions. So in the high frequency conditions, we can short all these capacitor. If you short all these capacitor, we will have only this resistor and resistor and inductive elements. Then we convert this Y parameter into Z parameter. If we convert Y parameter into Z parameter, from there we can start to extract this resistance and inductance. So if it is a Z parameter, so it will have a two part. One is the real part and the another one is the imaginary part. So in the Z parameter, the real part is the resistive component, and then the imaginary part is the inductive component. So these are all the just a sample parameter extracted from the flow that I said so far. So here is the physical interpretation of the S parameter. Here I have just listed two parameters. One is the S11 and then S22. It's just a reflection coefficient. S11 is the input reflection coefficient. S22 is the output reflection coefficient. So if you look at this curve, we can see the S11 and S22 are decreasing. Then after a certain point, it will start to increase. So in the low frequency, it is a capacitive effect. In the high frequency, it is an inductive effect. Then this is the point, it's a resonant point, where maybe it might be a resistive point or a resonant point, we used to say. So here, once we extracted and simulated this all S parameter and extracted the capacitance and everything, we simulate a noise figure in the ADS, and then we also simulate this noise figure in the TCAD. Then we start to compare, so we can see some good matching happening here. So in the ADS parameter extraction and modeling, we get S parameter, a characterized S parameter, and then that S parameter is loaded to the MATLAB. So from the MATLAB, we will extract all capacitance, inductance, resistance, everything we will extract. Then we will feed that values, capacitive and inductive values to the ADS simulator and then constructing a circuit there. So that will generate the noise figure. On the other hand, we have the TCAD simulation. So in the TCAD simulation, we will give a geometry, physics, then we do a simulation, and then we will get the noise figure. Then we can compare it. So we can validate like the TCAD simulation is equal to a circuit simulation, or circuit simulation is equal to a TCAD simulations. So when we do some research, so this is a kind of a research work. When we do a research, if you do something and if you are not sure on something else, we can do this cross comparison, and if they are matching, so what we are doing is the right. So next, a TCAD device simulation. So in the TCAD device simulation, as I said before, there are a lot of tools for a TCAD simulation. Synopsys and RS, Silvaco, then Crosslite Apsys. So these are all the TCAD tools. So in the TCAD tool, we can do two kind of simulation. One is a process simulation or a structural simulations. So if it is a device simulation, so this is the lower one is called as a device simulation. If it is a device simulation, we will give some structural informations. For example, what is the channel length? What is the gate length? What is the drain distance? Gate drain distance? What is the channel thickness? So all this information we have to give to this structural editor. If we give that information to the structural editor, we can create the structures. So then in the output of this structural editor, we will have some 2D MOSFET. So it will be like this. We will have some P substrate, then N plus N drain source contact, then we have the gate. So this structure is generated. So the structure can be generated another way. That is a process simulation. In the process simulation, we give some recipes to the simulator how exactly a transistor is fabricated in the manufacturing unit. So recipe in the sense, for example, if we take silicon, over the silicon we will grow oxide, or we will deposit oxide, and we will etch something, and we will again deposit something, then we do some annealing, and then doping. So in a structure, we just deposit oxide, doping. So all these things we have to give to the process simulator. Then the process simulator will provide the structure, and this structure is called a TDR file. Once this structure is developed, so it will be given to the device simulator. So in the device simulator, we have to give a physics model and then some material parameters. So physics model means like what is the mobility, electron velocity that we studied in electron devices subject we study, like energy band gap, then affinity, etc. Then so these are all the material parameters. Then physical model means there'll be an equation. So in layman language, it's just an equation. So we can see we might have seen some equation like a transport equations, or drift diffusion, continuity equations, etc. Even the Poisson equation. So all these input has to be given to this device simulator. Then the device simulator will take this structure and then solve these models with this parameter on the structure. So the whole structure is divided into a small rectangular or a triangular in each triangular, all this physical model or all these equations are solved. So this is the kind of how we do some mathematical equation numerical subject. So we will take a big equation and then we will break them into small pieces. Even we can have something like a differential equation and difference equations. So differential equation is more like a continuous. Differential equation is like a discrete or a digital one. So we'll break into small pieces. So like that, the whole equation is solved in every rectangular. And then from there, our voltage, our current, and everything is calculated. And finally, we will see the IV curve. For example, if we take a diode, it will have the voltage and it will have the current as well. So we can see a current is a more flat at some point start to increase. After the threshold voltage start to increase. So we can see such a IV curve. And then we do some analysis. Even we can do calculate the quantum efficiency also. In some LED light emitting diode, we can do some quantum efficiency calculation as well. And then in this tool, for creating these structures, so the TCAD will have some window, so where we can develop a structure by scripting, or there is some layout editor as well. So from there as well, we can make a structure. So the window looks like this. And here the calibration of the TCAD simulation. So in the simulation, the very tough and challenging part is the calibration. Because if you do a simulation and if there is a measured data, if our simulation result is not matching with the measured data, then whatever we do, it's just a useless. So first in the simulation, we have to match the hardware data. For example, if you do a circuit simulation, you will have a gain, there'll be a cutoff frequency, there'll be a power added efficiency, everything. If you take some research paper, you can see something like that. Some on current, some threshold voltage. So these things you can see in the research paper. If you want to improve some performance in the research paper, then first step, we need to reproduce the same result in our simulation. That is the first task. If you're able to reproduce the result of some good journal like IEEE, then some 80% of our research work has been completed. So that is the toughest part, even 90% I would say. So that is called a calibration. So matching our simulation result with the experimental result or the another research paper. So this is what I call a calibration. So in the calibration, so this is a simple MOSFET IDVD characteristics. So the x-axis is the VGS, y-axis is just a drain to source current. So we can see the drain current is almost flat till some point, then started to increase. So this is called a threshold voltage. And this has to be properly matched with the experimental. For that, we can do some tuning like a work function. So if you take any metal in a device, if you take a diode or transistor, there will be electrode like a drain, gate, source in MOSFET, then like emitter, base, collector in the BJT, then anode and cathode in the diode. So these are all the metal. So this metal can be a different material. The metal can be a aluminum, or it can be a gold, or it can be a copper, or it can be a nickel silicide, etc. So all of this material have some work function. So if you are able to tune the work function, we can tune this threshold voltage. Then channel. So from drain to source, there'll be a channel. So through that, the current passes. So the channel is open or closed. For example, if the device is in off state, the channel is open. When the device is in on state, the channel is, the device is in on state, the channel is closed from drain to source. So by adjusting the electrons in the channel, we can control the threshold voltage. Then this is just a buffer traps. So buffer trap in the sense when we do a manufacturing, there'll be a traps. So you might have seen something like in a diode transistor, there is a doping. Okay. So the semiconductor will be classified as intrinsic and extrinsic. So intrinsic means it's a pure semiconductor. When we add some dopant, it will become extrinsic. Okay. When we add a dopant in a semiconductor material, it's like just we're taking a gun and shooting in a wall. What will happen? It just penetrate into the wall or a human body. So it will go under damage. When we do some doping in a semiconductor device, it will damage the silicon part. From the damage, there will be some electron and hole or locked in intermediate state. They will not be in a conduction band or they will not be in a valence band. So this is called a traps. So by tuning the traps also we can do we can tune this threshold voltage. Next, the linear region here. So here we can adjust this portion by just simply tuning this mobility or velocity, etc. And as well as the channel electrons. So this is a calibration of a simple IDVG curve. Then if you look at this is the IDVD curve. So in the previous slides, this is a transfer curve. Transfer curve in the sense input voltage, output current, which is the input voltage, that is the output current. Then if we go to the output characteristics, we will have the drain to source voltage and drain current. So both of them the output parameter in the MOSFET. So here also we have a different region. So this is called a linear region. This is called a saturation region. So the linear region we can tune by low field mobility. Okay. So mobility means, for example, the electron will have a different behavior or different parameters called as like electron velocity, electron mobility. So electron velocity in the sense it's just directly correlative to the speed. Electron mobility means like it's just the electron will roam around. So this is called electron mobility. That is with respect to the area. So by tuning this mobility, we can tune the current in the linear region. And if you go to this saturation region, there are different things. High field mobility. High field mobility means mobility will not be affected much by the electric field. When we provide some gate to drain bias, there will be an electric field built between the gate and drain electrode or gate and channel. That electric field is a low or high. Its impact is a different at low electric field and a high electric field. In a low electric field or low gate voltage or low drain voltage, the electric field will not affect the mobility much. But in the high electric field, it will affect much. So even you can see the current at some point is a saturating and then it start to decrease. Okay, so why this current is a saturating fast? It's called a electron velocity saturation effect. After certain gate voltage, when the device is in on state, due to the high electric field, the speed of electron will be saturated. That's why we are seeing the same trend. The speed of electron increases when we increase this gate to drain voltage. After a certain point, the speed start to saturate because of the electric field impact on it. And then the thermal conductivity as well. When a current is flowing from one end drain to source, there'll be some heat. If the flow path is a very narrow and the current is very high, then we can feel the heat. Even in the modern computer, when we use a computer for the long time, we can see as a lot of current is flowing through a lot of device. Even that is also like on and off in a very short time. Too much switching and there will be a heat. So that heat also will affect our mobility. Then thermal boundary resistance, how the heat is dissipated. So that is controlled by the thermal resistance. So by using these parameter, we can control this saturation. So here in the bottom left figure, I just showing one of the simulated and experimental result. We can see the blue dot is the simulation and the solid green line is the experimental data. So we can see they are nicely matching. So in the previous slide and this slide, so why I'm just insisting much on this collaboration means in industry or in research, the collaboration is very much important. If you are not doing a proper calibration, then the work also will be useless. So in general, what industry will do, as I mentioned previously, to fabricate a device, or let us imagine some 1000 device in a wafer. Okay, today we just make a plan. We just make a plan for a device, many devices, and then we will make a layout, and then we will give to the some fabricating equipment, and it will fabricate a device, and we will see the result after 5 months or 6 months. Okay, so in the 6 months we have to invest a lot of time. Sorry, this is 6 months. Then we have to use some resource like some 20 engineers or 30 engineers to fabricate a chip with some 1,000 transistors. Two things mainly: time and the resource. 25 engineers, 6 month time. So simulation, the same result can be seen in 2 to some 4 weeks. Let us take half month to the max 1.5 month. So we can see the same result or approximate result in 2 to 4 weeks or some 6 weeks. Okay, roughly half month to 1.5 month. We do a simulation of a particular device, and then we will give a guideline to the device engineers. So they will fabricate the device. Instead of going and running a lot of real experiment or real fabricating device, they can reduce the design plan. Instead of using 1,000 wafer, they can use the 10 wafers. Instead of using some 100 engineers, they can use the 10 engineers. So further the simulation will assist. Okay, the question now, we do simulation and then they will fabricate the device. Whether the simulation result and measurement result are the same or not, that is the main question. If I'm working for 1.5 months and I'm just simulating a particular transistor and giving the design to the fabricating engineer or device engineer, he fabricate. Finally, the result is not matching with the simulation. Then my work is waste and his work also is waste. Okay, so for that, the calibration is very essential. So there will be some silicon data or hardware data already. We first match the silicon data and the hardware data in a simulation tool. For that, we have to do this calibration. If our simulation result is fitting with, let's take some, it has some 95% of fit with the silicon data, the pre-existing silicon or hardware data, then we can expect some 90 or 95% of the similar result after fabrications. Otherwise, if there is some gap between the silicon data and hardware data and simulation data, then there will be a risk we may not expect the same simulated result will be reflected in the real fabricated device. So that is the risk actually. So for that, the TCAD engineer, also, even you can take the device simulation engineers or the circuit simulation engineer, everyone try to match the hardware data. That is that will take a significant energy from the engineer or significant time as well. So that's why I'm just insisting this collaboration is very much important. Then in the simulation, if you take simulations, as I mentioned in the very beginning slides, there will be a lot of limitations in the real measurement. If one want to see the electrons inside the real fabricated device, how can we see? It's a very tough. Even in your laboratory, you can see a transistor. So what you will see? You will see some black color, some BJT transistor. It will have 3 electrodes, like a emitter, base, collector, and then there's some outer layer like a black color or something like some aluminum covering. So this is how you'll see. If you would like to see what is the doping inside, what is the electron concentration inside, what is the electron velocity, what is the electron mobility. So these things cannot be seen easily in a real time. So for that, the simulation will assist us. We can check the electron concentration and how the electron concentration is changing with respect to changing the bias. For example, here in the left figure, I am just having different voltage. The gate voltage is at 0 and then drain voltage at 4 volt. So this is called on state. And then in the off state, gate is very low. That is a less than threshold voltage. For example, if threshold voltage is a -4, then the gate voltage is less than -4, it's called off state. Then -8 volt, then 25 volt. Then again on state, 0 volt and 4 volt. So this is called a pre-stress and this is called a post-stress. So why I'm calling this a pre-stress and post-stress in the sense, here in the -8 and 25, we can see a difference. So 25 -8, the difference is like some 33 volt difference between the gate and drain. When we give a high voltage between the gate and drain, which means the device is stressed with high voltage. When the difference between the gate and drain is a low, the voltage difference, it is a low stress or a pre-stress. So when we give this kind of voltages, then pre-stress and post-stress, what will happen to the electron concentration? Okay, even for example, if you just in your laboratory, you just take a simple diode and then just give a connections like connect the positive to the anode, negative to the cathode, then just give some 1 volt and then connect one resistor with the resistor in series. I don't know how much practical in 1 year, but if you just give that connection for the 10 years, in the first year there will be a current. For example, the current through the diode may be 10 milliampere, but after 10 years or after 5 years, the current will not be 10 ampere. It can be something 12 ampere or it can be 18 ampere. It will be maybe increased or decreased. I don't know the exact logic, but there'll be changes in the current when we stress a device for the very longer period. When we do stress a longer period, then the performance or function of the device will change, and this is called a reliability. Even if you take some hardware, the performance in the first year will be very good. After 10 years, it will be different. It will perform very badly, and this is called a reliability. So when we give this kind of a stress, and if you would like to see something, what is happening inside this device, in reality or in practical, we cannot see. Still, if you want to see something in the real fabricated chip, if you would like to see what is the doping concentration, you have to take the wafer and you need to cut it. So we need to cut it, then we have to do some testing. Like there is something like a TEM is there. I think SEM is there. SEM is just for the surface. The TEM will measure over the doping profile, and we can see the doping profile. But if you just take the wafer and we cut the wafer, what will happen? We cannot use it again. Okay, a silicon wafer may be cost around, a small wafer may be cost around some 2,000 to 6,000. Some, if you take this GaN material, this is also semiconductor material. If you take this material, this wafer will come in lakhs. If I would like to see a doping in a gallium nitride based field effector transistor, I would like to cut the wafer, then only I can see it. If I cut it, then there will be a loss of 1 lakh or 2 lakh. So the simulation will help us to see the electron concentration without cutting the wafer. Till some point, engineers does not have any clue on something, even not from the simulation. In that case, they will go and cut it and see what's happening inside. So this is how these TCAD simulations help us. Then this is just a DC simulation in pulsed IV simulation, just result. So normally in laboratory we do DC simulation. So we just what we do, we just sweep the anode to cathode voltage and we measure the current. In the BJD, what we'll do, we just sweep the base emitter voltage and we will measure the collector current. In MOSFET, we just sweep the gate to source voltage and we will measure the drain to source current. So all of them are DC. So pulsed IV simulation in the sense, what will happen? Pulse means it's a kind of a pulse. You might have thing like a oscillator. There is analog oscillator and then digital oscillator. So in the analog oscillator, the output is like a sine wave, and then the digital oscillator, the output will be like a square wave. Okay, so that square wave is a kind of a pulsed IV simulation. The result of a DC simulation and then pulsed IV simulation are different, because in the pulsed IV simulation we just make the device on and off again and again. So in the off state, the device will be stressed a lot. When it is stressed a lot, there will be some electron trapped or catched by some traps or damage. When the useful electron is captured by some traps, what will happen? The current start to decrease. So we can see the difference in the DC simulation current and then pulsed IV simulation curve. So this kind of simulation also can be done in a TCAD. Then apart from this electron concentration, we can see the electric field. We can see the impact ionization. Impact ionization means, you might know the breakdown. There are different breakdown in a diode, like avalanche breakdown is there, Zener breakdown is there. Okay, so when the electric field reaches to a certain point, or every material will have some critical electric field. When electric field, we are giving high voltage, we are just sweeping the anode voltage from 0 volt to some 100 voltage. So when 0 volt to 100 volt, what will happen at some volt? For example, let's take some 20 volt. In 20 volt, the electric field inside the device will be very high, or the electric field will cross the material critical field. When it crosses the material critical field, the avalanche process starts. All of a sudden, you can see a large generation of the electron hole pair, and that's how the devices start to break. So that's called a breakdown. So we can also see the electric field impact ionization in the simulation. So this is also not possible in real fabricating device. Okay, so then how can we mimic a circuit in TCAD? So far what I explained, I just give some short. So in a TCAD simulation, in a short, so device engineer will make a plan and then fabricate a device that will take a 6 months. So to reduce the time, to reduce the cost, the same recipe is given to the TCAD, and we do some calibration, and then we will bring some result and we tell to the device engineer, you just go with these designs. This design in the sense you should have the N doping this much, P doping this much, and then gate length this much, anode distance this much, cathode distance this much. This kind of information we just pass to the device engineer. They will fabricate, and then if the calibration is good, then what is predicted by the simulation, the same will be reflected in the fabricated one as well. So this will save the cost, time, and then resource as well. So next, this is another work I have done in the past. How can we mimic the circuit in TCAD? So this is also one of the interesting work. Okay. So this work is based on a sensor. So we all know sensor like, for example, we have this IR sensor, we have the pressure sensor. Then we can also detect some species inside liquid. So there are a lot of sensors. So this sensor is just used to measure something in the fluid. For example, if you would like to measure a pH value in water, or if you would like to measure coronavirus in a liquid that's taken from our nose or from tongue, etc. So we can use this kind of sensor as well. The thing is that in the right side, this is used in one of the IEEE paper. So I have taken this circuit. So they have fabricated a device, and then they made a connection like this, and they used to measure some parameters in the liquid. So in my case, I don't have any real device. That time, even I don't have this circuit level software, etc. So I just want simulate this circuit, but in TCAD. So that's my task. So here it is a single transistor, and then there is a resistor. So the same circuit, I just made a layout here. So in the layout, you can see there is a gate 1, VG1, and then gate VG2. So this is a proper gate, and the VG1 is a proper gate, and VG2 is the fluid gate. So VG, yeah, fluid gate. So which means it is not conducting any semiconductor material. And then this is solution. So TCAD is capable to mimic the water as well. You can think if we take our saliva, we can mimic the saliva in the TCAD simulation. We can mimic the water in the TCAD simulation. So how we can do that? So TCAD, basically we can imagine the water as a conductor. Okay. Like even like cold water, hot water. So they have a different conductivity. Okay. Then we have the copper, semiconductor, insulator. Copper is a fully conductive. Insulator is a non-conductive. Semiconductor is a semiconductive. So as water has some property, the conductive property, we have 3 different material. You can also use this material to mimic that behavior. Okay, so what I did here is like I have taken a semiconductor material. Okay, for example, a GaN material, semiconductor material. And I want that semiconductor material to act as a solution or to act as a water. So for that, what I did, I changed the energy band gap between the conduction band and the valence band. You know, the energy band gap in the insulator is larger. For example, if you take a silicon dioxide or silicon nitride, they will have the energy band in the order of some 6 electron volt, 7 electron volt, etc. If you take the conductor, the energy band gap is a 0 electron volt. If you take the semiconductor, it can be 1 electron volt or it can be 3 electron volt. That's depending on the material. So one side semiconductor insulator is a 6 electron volt energy band gap, conductor is a 0 electron volt, and then semiconductor is a something like 1 electron volt or 1 electron volt. So in reality, we cannot set the energy band gap to be 0 for semiconductor. So that I just kept very low energy band gap, for example, 0.001. When I'm using the very low energy band gap for this semiconductor, it will act like a water. Even if you know the real conductivity of the water, we can try to bring the same conductivity in the semiconductor, then that also start to act like a water. So this solution is just nothing but the semiconductor region acting like a liquid region. So these two parts, for example, VG1, VG2, etc., all this part I made like this. And this is called a non-linear resistor. So you know the resistor and then non-linear resistor. Resistor, for example, transistor and then resistor. So what is the difference? Resistor will have a lumped resistance. Okay. Then transistor is a non-linear resistor. It will behave like a resistor, but the relationship is not a linear. For example, if you take a resistor, V equal IR. If you increase the V, your I will increase. So this is the linear relationship between the voltage and current. So that is the theory behind this resistor. But if you increase the voltage and if you check the current in the MOSFET, the relation is not linear. You can see, for example, till the threshold voltage, you will see the 0 current. After the threshold voltage, you will see some current with some slope. Then after some voltage, again you see the another current with some other slope. So each and every point you will have a different slope of current with respect to the voltage. So that's why it's called as a nonlinear resistor. So this section is simply mimicked by the figure in the left side. But this circuit can also be simulated in the TCAD. But the problem there, like a conversion issue. If a simulator, for example, if a simulator purely simulating a circuit, and then it is a simulating a device, or it can simulate both the device and circuit, even it can have like a electromagnetic simulation that's very complicated. We can have a device simulation, we can have a circuit simulation, we can run some electromagnetic physics behind that. When we add a lot of simulation together, then the problem is that we cannot run a successful simulation. There'll be some conversion issues. So that's why I want just some 2D simulation for this structure. So this nonlinear part is just mimicked by this figure in the left side. Then I want this resistive part. So for that, what I did, I just added another resistive semiconductor region. Here you can see some gray shaded region. This is mimicked by this rectangular region here. And then from there, you can see some light magenta region. So this is the mimic for this resistor RD, or a drain resistance. So this resistive region is nothing but a semiconductor only. But what I did, if you take a semiconductor, let's imagine an intrinsic semiconductor. Intrinsic semiconductor will have a large resistance. If I want to reduce the resistance, I can add a doping in the order of 1:17, 1:16 atom per cubic meter. Then the resistance, for example, in the intrinsic, the resistance is a 1 ohm, sorry, 10 ohm. If I add a dopant, that is a 1 is 16 atom per cubic meter, then the resistance from 10 ohm it will be reduced to 8 ohm. Even if I add 1e18 atoms, it will be reduced to 6 ohm. Again, if you add 1 in 19 atoms, again the resistance start to reduce. So by doping, we can change the resistivity behavior of the semiconductor such that we can mimic the resistance. So this is how I mimicked it, and then I supplied the VDD here, and then I took this V out from this drain electrode. Even this is what this was not even a direct one. So I am not able to take the output voltage directly from this drain electrode. So what I did, if I make a connection here, there is some initial solving in the TCAD simulation, or even if you take any circuit-based simulation or TCAD device-based simulation, there will be some initial solve. Initial solve in the sense all electrode will be applied with a zero bias. Because of that, I am not able to take the output voltage from this drain electrode to mimic this circuit. So then I fixed some probe below this drain electrode. I am able to measure that one. So this is how I made this circuit. Then again, this is a potential graph, output voltage. So we can see the different things like pinch off region, transition region, on state region. So in the on state region, output voltage is 0 volt. In the pinch off the region, output voltage will be high. So you can imagine what will happen when this device is turned on. When this device is turned on, this D is shorted to the ground, then the voltage at the D is 0. And the device is off state, the D and this ground are not shorted. So whatever we are giving in the VDD, the same will be reflected in the V out. So that's why we are seeing this kind of graph. We are seeing the pinch off region. We are seeing the higher voltage. In the on state region, we are seeing the low voltage. Then this is a transition region. Okay. Then in the right side, we can see the potential. So as I mentioned before, we can also see the potential distribution inside the device. It's not easy to see in the experimental again. So in the on state and off state, we can see the most of the potential is distributed in between the gate and gate edge. Okay, we have a different edges here. Imagine this point is one edge and this point is another edge. Okay, in one edge, for example, the green line, we can see lot of potential is dropped in gate edge when device is in off state. When device is in on state, the potential is dropped in resistive region. You just look at this figure, and if the device is on, this is shorted. So all potential will be dropped in resistance. If the device is in off state, all potential will be dropped between the drain and source of this device. That's why we are saying in on state, all the potentials are dropped in device. Sorry, off state, all the potentials are dropped in device. In on state, is dropped in resistive region. So this analysis also can be seen in the TCAD simulation. This is not easy in experimental at all. Yeah, here, here I'm just showing how it is mimicked. In a reality, if I would like to measure the pH value in a liquid, pH value in the liquid, let us take a liquid, and this is the liquid, and this liquid is mimicked like this: GaN cap layer, silicon oxide layer, some stun layer, electrolyte layer. So this many layers is used in the simulation to mimic the exact liquid. Then pH. So in the water, there will be a different pH value. So how we can mimic the pH value in a device simulation. For that, we can use a different interface charges. Okay, like between the gate and the drain, or between this gate and the electrode section in the simulation, we can fix the different charges in the order of 1.80, 1.84 E12 in the sense the pH value is equal to 7.9. Then if it is a minus 2.21 E12 in the sense, it's a 8.4. So I changed this interface charges to mimic the pH value in the simulation, and then measured the output characteristics. So we can see a different transferred output characteristics with a different pH value. So this is how I mimicked. And okay, then the left is the conventional one. Then from there, I need to go for a proposed structure so that I can publish a paper. So when we target for some research paper, I have done all the work that is existing in the IEEE journal. Then I mimicked. I took around 4 to 5 months to bring the same result of the IEEE paper by using the left side structure to have a different output curve for a different pH value. Okay, so the POR is ready. POR or the base or the conventional was ready. Then from there, I need to propose something new, and then it should have a better performance. So for that, I just simply added another semiconductor material, so this back barrier. It's nothing but an argon layer. If you look the left side, from this region to this region is full of gallium nitride. I simply used a back barrier region or aluminum gallium nitride region as a proposed structure, so that I'm able to improve the performance of the proposed structure. And here is some basic result without back barrier, argon with argon back barrier, with aluminum nitride back barrier. So different kind of back barrier. I used a different semiconductor material. One is aluminum nitride, one is aluminum gallium nitride, another one is the p-doped gallium nitride, different semiconductor material. And then I just plotted all of them and verified how they are varying. I'm changing different back barrier material. And then the right side is just energy band diagram. And this region is of interesting region. So some of you might have heard the quantum well or quantum theory. So in semiconductor device, we will have channel thickness. Okay, when the channel thickness goes lower than 5 nanometer or 6 nanometer, then our conventional theory or the physics is not a classical one. When the channel thickness goes below 6 nanometer or 5 nanometer, the physics is no more classical one. It became a quantum behavior. The electron start to behave like a waves. And we can see this region having some thickness of some 10 nanometer. So if I don't have the zoom to plot here. If you zoom the region around here, we can see the quantum well. Quantum well means where the electron go and confine. So electron always stay at the lower energy. You see a common correlation. You can see a conduction band, valence band. You can see all of the electron in the conduction band. When the electron gets energy, it goes to the conduction band. So if there is no energy, they will stay at the lower energy level. So we can see the energy band diagram. So all of the electron will stay here, and this is called a channel region. In there, this quantum well, the shape changing. For example, when I'm changing this back barrier material, aluminum nitride or argon or a pGAN. When I change this, the shape of the quantum well changes, which means the well thickness changes. Well thickness is vary from the 6 nanometer to 5, 5 to 4, 4 to 3. When the well thickness changes, then I have a better control over the channel. If you have a channel thickness of 10 nanometer, the gate need a more energy to control the channel. If it is a thin channel, the gate can easily control the channel. So by adjusting the quantum well shape or quantum well thickness, I am able to have a better control over a channel, such that I am able to improve the sensitivity. So here you can see the x-axis pH, y-axis the output voltage. Here you can see this blue aluminum nitride back barrier, then this red aluminum gallium nitride back barrier. So this red and the blue are overlapping. You can see the conventional one or the measurement or the PUR case without back barrier is here, and we can see the blue and red are here. So the changes in the output voltage is more for argon back barrier and aluminum nitride back barrier, which means the sensitivity is higher. Even I just listed some literature work. So some papers I have taken, some 10 papers, and then listed the sensitivity. So this is the PUR sensitivity, 2060 millivolt per pH. When there is a change in pH, for example, the pH is a change from 1 to 2, the output voltage will change for 2060 millivolt. And the other reported work also having here. And the 10 is the number 10 is the PUR for me. And then here in the bottom you can see the improvement in the sensitivity. When we change the pH value from 1 to 2, the change in output voltage is 2384. So this is how I improved the sensitivity. So in this work, the conclusion is like we can simulate a sensor in TCAD. Number one. Number two, we can mimic a circuit in TCAD. Number three, we can mimic a resistor in TCAD. Number four, we can mimic a liquid or water in TCAD. Then we can mimic the pH value. So these are all the things can be done in TCAD. So this is the conclusion of this one. So these are all the references. So I don't know, there are no more slides. I'm almost at the end. Sir, I
Yes,
just
sir.
finished some 10 minutes earlier.
Okay, no issues, sir. No issues.
I don't know how the audience enjoyed this one because it's a
Yes, sir, sure.
very raw.
Definitely, the audience are enjoyed your session, sir. Thank you, Dr. L. Arivalagan, sir, for delivering such a valuable and industry-oriented session on EDA and TCAD tools. To deliver the vote of thanks for this session, may I now invite Dr. S. Mahendran, sir, HOD of Electrical and Electronics Engineering Department, to address the gathering.
Am I audible, sir?
Yes, sir, audible.
Yes.
Good evening to one and all present here. It gives me immense pleasure to propose vote of thanks for this wonderful session. I take this opportunity to thank our today's subject expert, Dr. L. Arivalagan, sir, Principal Engineer, Global Foundries, Karnataka, India, for his wonderful session on electronic design automation and technology computer aided design tools in semiconductor circuit design. Sir, your industry insights and detailed explanation of advanced design and simulation methodologies were highly valuable for us and added a strong practical dimensions of this session. On behalf of organizing team and all the participants, I sincerely thank you for your time and contribution to the success of day 2 of our ATAL FDP. Thank you, sir.
Yes. Thank you.
I
Welcome.
also thank you, sir. I also thank Dr. Kannan sir, our chairman and principal ma'am for this wonderful FDP to our participants. I also extend my sincere thanks to all the participants who spend their valuable times to enrich their knowledge. Thank you all. Thank you very much for the opportunity given to me. Once again, thank you all.
So thank you, Dr. Mahendran sir, for your thoughtful vote of thanks and for gracefully concluding this session. With this, we have successfully concluded day 2 of our ATAL FDP. We sincerely thank both of our eminent resource person, Dr. Jobin Varghese and Dr. L. Arivalagan, for their rich contributions, and we extend our gratitude to all faculty members, participants, and supporting staff for their enthusiastic participation. We look forward to our active involvement in day 3, which will focus on embedded and intelligent integration, featuring 2 more interesting sessions. Thank you all once again. Have a pleasant evening. Dear participants, I will share the feedback form for this session in our WhatsApp chat as well as the chat box of our Google Meet. Along with, I will send the details regarding our technical session for resource person for contacting him for any queries if you have. Thank you once again. Have a pleasant evening. Thank you. Thank you, sir.
Thank you.